This is section 12.3, geometric sequences and series. We're going to begin with talking about what a geometric sequence is, and then we will be identifying specific and general terms of the geometric sequence. Let's take a look. This first sequence shown is an arithmetic sequence, and this second sequence is a geometric sequence. And as you can see, in the geometric sequence, we do not have a common difference. It is changing, but here we do have a common difference. So you can definitely see that they are two different types of sequences. So let's go ahead and define our geometric sequence. And a geometric sequence is as follows. A sequence in which each term after the first is the product of the preceding term and a fixed non-real number called the common ratio. So instead of a common difference, we're going to have a common ratio. And here we have a common difference, D. In the arithmetic. Move that over. Okay, so how do we find this common ratio R? R is the common ratio. Whoops. So, how we find the common ratio R is we take a look at the first term and the second term and the third term, if you can see. And as you can see here, this term here is the previous term times R. And this is the previous term times R again, and so forth. So each term, you can see here A sub n, is the first term A sub 1 times that common ratio to the n minus 1 power. Let me write that a little bit bigger. So you might hear me say A R to the n minus 1. We really mean A sub 1 times R to the n minus 1. So how could you find R? You could divide any term after the first term by the preceding term. And that's how you can come up with R. So that's pretty easy. So as you can see, 16 divided by 8 is 2. So R is 2. Here we had 4 minus 2 is 2. So D is 2. Okay, let's take a look at number 1 and 2. And here we're going to determine whether the sequence is geometric or not. So we're going to do what we said. We're going to take a preceding term, a future term, and divide it by a preceding term. So we will have 6 divided by 2, and that's equal to 3. Let's try the third term divided by the second term. 18 divided by 6 is 3. So yes, R is 3. So this is geometric. And you could check the next term also. You can see 54 divided by 18 is 3. Okay, let's go ahead and take a look at number 2. A sub 2 divided by A sub 1 is 6 divided by 2, and that's 3. A sub 3 divided by A sub 2, 10 divided by 6, that's 5/3. So these are not equal. So no, this is not a geometric sequence, okay? That common ratio has to be the same. So now here we're going to write the first 4 terms of a geometric sequence. They give us A sub 1, and they also give us the common ratio. So let's write this down. A sub n is equal to A sub 1 times R to the n minus 1. So A sub 1 is the first term times 4 to the 0 power, 1 minus 1 power, which is 0. And that's going to be negative 2. Likewise, the second term see if I can move this up a little bit, is going to be equal to the first term times 4 to the first power, and that's going to be -8. And you could keep going. So here, since it's the third term, we're going to square 4, and we're going to have -32. And our fourth term, -2, 4 cubed, and that's -128. And as you can see over here, we have these terms plotted, and you can also see this function created from the terms of the geometric sequence. Okay, so now let's go ahead and write a formula this time for the nth term, and they give us the sequence. Okay, so why don't we just take a sub 2 and divide it by a sub 1, and we will get 4/5. We can go ahead. They did tell us that it's a geometric sequence, but we could just go ahead and divide a sub 3 by a sub 2 to double check. That's 16/5 divided by 4, and that's equal to 16 over 20, and we get 4/5 again. So we know now that R is definitely 4/5. So we have a sub n is our first term times R to the n minus 1 power. And that is the formula for the nth term. Okay. And again, this is a sub n is equal to a sub 1 R to the n minus 1 power. Here, we're asked to find the sixth term of a geometric sequence, and they give us a1 and a sub 2. So what could we do? We could immediately, if it is a geometric sequence already known, we could have a sub 2 divided by a sub 1, and that's 12 divided by 10, and that's 6/5. So R is equal to 6/5. So now we could have a sub n is equal to a sub 1 R to the n minus 1. So a sub 6 is equal to 10 times 6/5 to the 5th power. And if you put that in your calculator, you should get a big number, 15,552 in the numerator, divided by 625. And that is a sub 6. I think I might move that down here. Okay, now in number 6, we're going to find R, a sub 1, and an expression for the nth term when they give us a sub 4 and a sub 7. So we have a little work to do. So the first thing we want to do is write our formula. And as you can see, we know that a sub n is a sub 1 times R to the n minus 1. So let's write a formula for a sub 3, a sub 4. A sub 4, the fourth term, is the first term times R cubed. So we know that a sub 4, negative 240, is equal to a sub 1 R cubed. So now I could actually say that a sub 1 is equal to negative 240 over R cubed. So make sure we hang on to this value for a sub 1. Okay, let's do the same thing. A sub 7 is equal to a sub 1 times R to the 6th. And they gave us a sub 7 is 1920 equals a sub 1 over r sub 6. So we could use substitution, or we could have put these two together. It doesn't really matter, but let's just go ahead and continue with what we were doing. We will now substitute in this a sub 1, negative 240 over r cubed times r to the 6th. And as you can see, we will be left with 1920 is equal to negative 240 r cubed. So r cubed is 1920 divided by 240. Negative 240. So r cubed, and if you divide that out, you'll get a negative 8. So r is equal to negative 2. So we have a lot going on. So now we've found r. We do not have a sub 1 yet. So we can now find a sub 1 is negative 240 over r cubed was negative 8. So a sub 1 is going to be 30, positive 30. Okay? And now all we need is a sub n. So a sub n is equal to a sub 1 r to the n minus 1. So a sub n is equal to negative 240. Whoops, a sub 1 is 30, sorry. 30 times negative 2 to the n minus 1. And there we have a sub n. So a little work, but each item, each value, a term that they give us helps us find what we need. Okay, bring that up a little bit. Okay, now let's evaluate a finite geometric series. And we will be coming up with partial sums. So the formula for the partial sum of the first n terms is equal to the first term times 1 minus r to that nth power divided by 1 minus r. Okay, so let's go ahead and see if we can use that formula. If we want to find this sum, keep in mind, if you could see this, a r to the n minus 1. If you can kind of see this comparison. So with that, you should be able to see that a sub 1, is equal to 3, and r is equal to negative 1/3. So with that, the sum of the first 8 terms, and here n is 8, so now if we want to find s sub 8, we will have a sub 1, 1 minus r to the 8th power divided by 1 minus r, and we come up with 3 times 1 minus, and here we'll take a negative 1/3, and we are going to raise that to the 8th power and divide by 1 minus a negative 1/3. You will have to do a little bit of math there, and also your frac on your calculator. So make sure on your calculator you use math frac to get this fraction, okay? That's really important. I'm going to bring this over. And that's what we have. That is the sum of the first 8 terms, s sub 8. Okay, Now, let's look at number 8. And in number 8, we're asked to find the sum of the finite geometric series. So we don't know, well, let's write a few things down first. Let's first find r. So to find r, we will have a sub 2 divided by a sub 1. So that's 6 minus 3 is 2. So now we know that r is equal to 2. And we were told that this was geometric, so we could just make that ratio between the first two terms. So now we don't know what term this is. Here we have to find n. So in order to do that, keep in mind that we have a sub n equals 3, which is a sub 1, times our ratio to the n minus 1 power. And they gave us this 1536. We'll divide both sides by 3. And 512 is 2 to the 9th power. So we know that 9 equals n minus 1, and n is equal to 10. So now we will find S sub 10. So S sub 10 is a sub 1, 1 minus r to the 10th power divided by 1 minus r. So S sub 10 and a sub 1 is 3 times 1 minus 2 to the 10th power divided by 1 minus 2. And if you work that out, you will get 3,069. Okay, now we are going to find the actual sum of an infinite geometric series. So infinitely many terms, and we can find that sum. Now, we can only find the sum if the common ratio absolute value is less than 1. Only if the absolute value of r is less than 1. If the absolute value of r is equal to 1 or greater than 1, then the sum doesn't exist. Okay. Find the sum if possible. So we first need to find the absolute value of r. So the absolute value of r is the absolute value of negative 3/5. That's equal to 3/5. It's less than 1. Check. So the sum exists. So the sum is a sub 1 over 1 minus r. Our first term is negative 6, 1 minus 3/5. 1 plus 3/5 because it's 1 minus a negative 3/5. You'll come up with a negative 15/4. So that is the sum of that infinite series. Okay, let me fix this here. Okay, let's do the same here. The absolute value of r, you can see here if we take a sub 2 divided by a sub 1, and we have a negative 3/2. Well, the absolute value of r is equal to the absolute value of negative 3/2, which is equal to 3/2, but that's greater than or equal to 1. So the sum does not exist. We can't find that sum. Okay, let's look at a really cool problem. So here they've asked us to write 0.045 repeating as a fraction. And let's talk about what that means. That's 0.04 5, 5, 5, and so forth. And that's actually equal, I don't know why I changed to that color. Let me just erase that. So that's equal to 0.04555 and so forth. Well, that's equal to 0.04 plus this infinite sequence. So this right here is our infinite series. And it's geometric. So now we could write that this is equal to 4, why that cat keeps happening, equal to 4 over 100 plus, and now we have to write what this is. So let's go ahead and come over here, and we have 0.00555 repeating, and that's equal to 5 over 1,000, that's this first 5, plus 5 over 10,000, plus 5 over 100,000, plus on and on. So what do you notice? 5 over, what do you notice between these two terms here? Here we have a geometric series with A equal to 5 over 1,000. And as you can see, this term, each term is multiplied by 1/10. So you can see here, if you multiply this by 10, you get this. Multiply this by 10, you get this. And so forth. So you should be able to see that that ratio, common ratio, is 1/10. So how could we find what the sum is here? This sum is equal to that a sub 1 over 1 minus r. So 5 over 1,000 divided by 1 minus 1/10. And I did this out, which is 1 over 180. So that's where we get 1 over 180. And if you get a common denominator, you will get 41 over 900. And that's actually what 0.045 repeating is. So let me just put a little star by this, and I'll give you a star here. And that's where we came up with that 1 over 180. Okay, we will now look at a couple application problems before we finish this section. And the first is the multiplier effect. The federal government will give a tax rebate of $1,500 to every individual filing federal income tax. Suppose every person receiving the rebate will spend 70% of that $1,500 and save 30%. The money spent is respent again and again by other people and businesses at a rate of 70%. Determine the theoretical total amount of money spent from the initial $1,500. And we will assume the money can be respent an infinite number of times. So let's take a look at this. We'll start with $1,500, and then we have 0.7 times $1,500. And then we have 0.7 times 1050 plus dot, dot, dot. So as you can see right here, here we have 1050, and here we have 735. And all this is 0.7 squared times 1500. And this was 0.7 times 1500 to the first power. Okay, so that leads us to be able to say that a sub 1 is 15 and that common ratio is 0.7. So if we wanted to add all of this up, I equal 1 to infinity. So we'll be adding up an infinite series. We have 0.7 to the I minus 1. And we just learned here, since R is equal to I'll write it here, since the absolute value of R is equal to 0.7, which is less than 1, the sum of the infinite geometric series exists. So we can find that sum. So I won't write it right here. And so now we will have that sum is 1500 a sub 1 over 1 minus R. And we will have $5,000. Okay. Let's take a look at some formulas to find the value of an annuity. Remember that if P dollars is invested at an interest rate of R, here's the interest rate of R, and compounded annually for T years, then this is the amount that you will have after T years. However, rather than making a one-time lump sum payment of P dollars, many individuals will invest smaller amounts at a regular, more frequent intervals. And those are called annuities, and they are over a fixed period of time. So the future value of an ordinary and an annuity is given by this equation. Now our variables have not changed. T is going to be time in years. P is the number of dollars invested. We are compounding n times per year. R is our rate in decimal form. And A is the amount of the annuity after T years. So suppose that you deposit $100 each month into a tax-sheltered annuity, paying 5.8% compounded monthly. So let's just see. Our principal amount is $100. Our rate is 0.058. And they have said here that we are compounding monthly, so N is 12. If you began paying at age 23, what would your annuity be worth at 65? So the time is going to be over this period that you went from age 23 to 65, and that would be 42 years. So with that, the amount of the annuity is 100, and then we will have 1 plus 0.058 compounded 12 times, so divided by 12 times a year, 12 times 42 minus 1. All of that is in the numerator, so you will have to practice with your calculator. Make sure and then in the denominator, we have 0.058 divided by 12. So you should get an amount of $214,000, $352.70 at the end of those 42 years. And that concludes this section.